All right, so let's set up. All right, 10 persons online, which is a good start. And still missing the board. All right. Let me switch the screen now. All right, so I want to get a good vantage point for this because, all right, we want to get the measurements here. All right, now there's a feature here to record data. So if we, this is, and that's a table here. Then they call it P and Q, but that's your thing. You click record data when you have something. So we're going to here now. The instructions. We can click here for instructions. Then say, all right, let me say choose one lens available from the drop-down list. All right. And next one says if you can't see the image. All right, they're using P and Q, just like P would be like U, and V, sorry. Yeah, P would be like Q. All right, what am I say? Hold on there. If you can't see the image for the arrow, then the lens is at a distance P smaller than equal to the focal length. All right, you see that? We mentioned this last week, or in class this week, I should say. All right, if you cannot see the image for the arrow, so if you're looking at this, guys, you're seeing the arrow right now, right?
Yes, sir.
All right, so remember now the object is here, all right, and the light is leaving the object, passing through this lens here. At the moment, it's 54.5 centimeters away from the object. So the lens is there. Light passes through the lens and refracts onto this dark screen. All right. No, there's an arrow there, which means, and this this information is saying if you can't see an image for the arrow, then the lens is at a distance P smaller than or equal to the focal length of a lens. All right. Look at this. Move the lens away. And so you're going to move the lens away. All right. Always search for a well-defined image. All right. And of course, note the size of the arrow. You're going to look to see if it's bigger or smaller. Any questions here, guys? All right. So there you're looking at it. So the arrow is here as the object, and image is there. So what could happen then is if we move this lens closer, notice that, remember what you notice happening to the object, to the image.
It's smaller and larger. When you close a magnifying glass, the object get larger, but the further definitely object gets smaller.
Gets smaller. Yeah. All right. I hope everybody's seen that. So pretty much now we're just going to measure these distances and see what happens there. Now, the previous instructions say that we must always adjust the lens so we can get a sharp image. All right. Now, a sharp image, what looking at? Always search for the well-defined image of the arrow. Well-defined means it's not blurry and everything there. Like this. This is blurry, you know. This is not well-defined. But you seen that?
Yes, sir.
Yeah, it's not well-defined. You want it because this is what the object look like. Nice bright yellow arrow towards the left of the screen. But then coming across now, this thing here, this image is blurry. So what we'll have to do is adjust it until we get a sharper image, or the sharpest possible image, which, well, that's blurry, magnified here, and this looks kind of well defined there. And of course, we have to note the size. So objective here, guys, again, is to find the focal length of this lens. Now, let's say the lens stays there. All right, let's zoom out and see how far we can actually And this is actually called an optical bench. In a real lab, it's referred to as the optical bench. I don't know if any of you guys who go to high school would have it. You see anything like this at Manchester, Benito?
I don't think so. I might think almost a hit.
Oh, well, possibly. Dijane, anything like this at Bishops? Or you don't get to use the lab yet?
No, sir. And I don't go to Bishop, sir.
Where you go?
DC.
DC you go? Alright. So, they have anything like this there?
No, sir.
Nothing. Are you sure? Well, I'm not sure that they had. Unless, you enter the lab already at DC?
Yes, sir.
Okay. Cool. That was, you mean since fourth form?
Sir, since third form.
You get to choose subject in third form?
Yes, sir.
Okay. All right. Well, what about anybody else ever use anything like this? Dwayne or Michaela, Marlon, Kayla, Janari?
Said, sir.
You say Marlon?
No, sir.
No. Which school you go? All right. Okay, well, stressing that most. All right. Well, this should be in every high school lab. It's not the cheapest thing to get, but certainly important. I'm just trying to see here what would happen. I'm keeping. All right. So the image, because it have a maximum distance here, and let's see if we can zoom out so we can see what's happening here. Look at that. See what's happened there? So magnified until it just disappear. All right. You know what's happening there. I have to measure these distances here. All right. So this now, all right. So this is the object here. And the lens is 0.1 centimeters away. All right. If we, if this is telling us something, you know, guys, look at that. We're adjusting the lens until we don't see an image. And the point where we don't see an image is about the focal length of the lens. So watch that now. We see that image there. And then all of a sudden it gone. That's saying us something. That's telling us something about the power of the lens. Could this be the focal point or the principal focus of the lens? Want to find that out. What's the focal length of this lens? All right. When compare object distance with image distance, record the results. All right. So now, so let's begin now. All right. Now as per the instructions, moving this away. Let's use. I probably could use 0.1. We're going to start with the largest distance first. And what we're going to do here, so what we could do is probably move this and see where the image is formed in each case. So we have to go vary this distance. So guess what we're going to know? We're going to mark out like, so this is, let's say that this is 9 centimeters. Could you do it for 5? We're seeing that we have only how could I do this now? Probably can't do it for 5. So we can do it like every 5 centimeter. And then we can want something more easy for plot. So we could have started at like something like close to 5. And then we'll go up by probably 10 if you allow it. Let's try 5.3. All right, so we're going to start from a small distance, guys, as small as possible, and we work way up. And what we're actually varying now is the distance of the object from the lens. Everybody seeing that? All right. We are going to vary the distance of the object from the lens. The object is here on the left-hand side where the mouse is pointing on. As you can see, it's plugged into a socket here. All right, so this is where the object, this is the source of the object. All right, the distance between the object and the lens is 5.3. So in the table, you'll write that under the letter U, or distance of object from lens, not screen. So there are some errors in that lab sheet, and I'm going to change it and send you this one after we finish. So all right, the distance of object from the lens is 5.3. All right, at the moment. We are going to locate the image, the distance of the image from the lens. So distance of the object is 5.3. What is the distance of the image? You could calculate it if you know the focal length of the lens. So, and because we don't know the focal length of the lens, we are going to have to try and find it. So, hence we're doing this lab. We are trying to find out how powerful this lens is. And then there's no image. You see that we're moving this thing. There's no image. And let's zoom out. But you seeing that, guys, we're not getting any image at all. We carry it close here and we're moving it further away and there's just no image. So where's this image? Where's this image? Where's the image? No image being found here at 5.3. What is that telling us about the lens?
Too close, lens, sir.
You said object too close to the lens?
The lens too close to the object, sir.
Lens too close to the object. That's a good way. That's a good, yeah, that's a good reasoning to start from. Anybody else? We learn something else too. If we're not seeing an image, what does that tell us about the lens? Right?
There may be something them to, sir, like it's spread far apart because the lens too close to the object, so it's spread far apart, it's not focusing.
but then no, Jenna, if you say that the light from the object will go pass through the lens and focus somewhere, some distance before it. So you're saying that it's spread far. What is spread far apart? The light from where? Which? So, all right. So at the moment now, this lens is working properly. We know that. We see that images are found on the screen. So nothing is wrong with the lens. Nothing is wrong with the object. Nothing is wrong with the screen. All right. So we are certain that light is passing through the lens. Yes, go ahead, Chanel.
Refracted rays are parallel.
Oh, refracted rays are parallel. Yeah, you're getting a bit warmer there. I like that. So Janari started out pretty well, and then you're helping him out there now, which is good. You're saying that the refracted rays are parallel. That is indeed correct. As Janari was trying to say, they spread far apart. You should have said that they were parallel. The rays them spread so far apart, I just say. Parallel rays don't refract, they don't meet. So therefore, if we go back to that diagram that we did, I don't know if I can find that diagram, but it's in the group. Let me see something here. And so it'll be, I want to share this because so I don't need to take up on a book because we do these things in class. And I wanted to go back to the notes here. All right, this, hold on a sec. Why is it not there? All right, because that same image that I sent you guys, it's the one that at the one with the 5 instances. Let's go back to that. Oh wait, no. And change the screen. New share. All right. So looking at this now, everybody seeing this?
Yes, sir.
Mm.
Sir.
All right. So let's go back to this theory here. We've seen here that, all right. Look at number 4. What does number 4 say?
Object at F.
No image, refracted rays are parallel.
Mm-hmm. You see that? That's it. That's the only case we see here where there's no image. Interestingly, you put the object at the focal length. Now, bear this in mind. This is telling us something that is actually telling us that we are close. When we're not seeing any image, it's telling us that we are close to the focal length of this lens. But you see that?
Yes, sir.
Yes, sir.
Yeah, we are close. So now we are, if I go back to this now, it is at currently at 5.3. It means that it's close to that. No, because then if it was nearer, I'm going back to the original image. If it was nearer, or they say between the focal length, between F and the lens, they say that image would be virtual, and so it could be that there's an image, but it's not on the opposite side. So when you look at number 4 and number 5, that is what's happening now, guys. But you see that?
Yes, sir.
Right, number 4, there's no image, period, no image at all. But for number 5, the image is formed, but it's on the same side as the object. Right now, because the screen is on this side, we won't be able to see it. So at 5.3, we're not seeing an image, either because we are at the focal length of the lens, or a virtual image is formed that the screen has not detected. All right, that's it. So hope you understand what's happening here. All right, but we're still going to account for it in the sense that when put it in, and then we're not seeing an image distance there. So therefore, if we go to the table, see if we can find the table that we're writing up with information in, and put the 5.3 there. But we're not seeing an image form. So unless know what would happen here, unless we're going to go behind, which I don't know if this can move. It can't move. All right. No, it can't move. So again, that's one of the limitations of it. You know, to find this image, you probably would have to go put a screen behind the object, you know, and you would probably see it. Yes, how these things work. All right. Now, if we're doing this lab in real life, that's what we'd actually do. It does look like magic because you're shining a light through a lens, but yet the image that you're seeing is behind the object. You know, it's just amazing. So we're not seeing any image here. So this would be out. This will be out. Anyway, right, no image. I hope everybody understand what's happening here. All right. It's going to be 1 over 5.3, whatever that work out to be. All right, that's 1 over u. But then there's no image. No image, guys. All right. So, any questions at this point?
No, sir.
All right, good. So, let's switch over then and continue with this. All right, let's close this. All right, so at 5.3, nothing. We're going to probably move it, and then I'm wondering though, in terms of the increment, we probably might want to move it at small distances. So if that works out for us, we might write it as a precaution or as a source of error that we move the length away from the object in small increments. Let's see if that works out for us here. All right, so at the moment you're seeing it at 5.3. no image. Just confirm that. Let's zoom out and confirm that there's no image. So we're on the right track there. Let's zoom in now. All right, what we're gonna do here, we're gonna increase the distance away from the lens, because seeing that we're probably close to the focal length of the lens, we want to take our time. And let's move it to about, say, 6 point, well, let's see 6. Can I get 6.3? I'm not giving me 6.3. Another limitation now is that the sensitivity, the sensitivity of the mouse when moving this is a variable. So when we write those things, those are your limitations. Sensitivity of mouse or cursor. All right, so sensitivity of the mouse or cursor. That might just affect this in the virtual world. All right, at 6.4, we originally started, because I would have wanted to see like 6.3, so that we can move up by 1. But all right, 6.4 is close enough. Because you can round it down to 6. All right, so it's 6.4 now, guys. Let's see if we see an image from on the screen. And it seems like this is a no-show here. Nothing here, guys. Nothing at all. At 6.4, there's still nothing. All right, this is interesting. Where is the focal length of this image, of this lens, I should say? All right, so now nothing, no image form. Repeating that in the second table or second column. All right, so now let's increase this now. Let's move this to like 7. All right, probably 7.1, 7.2, 7.5 now. Let's try 7.5. All right, 7.5. Is it 7.5? I believe I have an idea where it is, and so probably I'm purposefully doing it this way, because I know we're probably close. It's somewhere out there, but it's good for us to do it this way, so we know how lens work. All right, these are the little things that the ophthalmologists, the optician, persons who deal with these things, they do it to fit the perfect glasses for your eyes. So a lot of testing has to take place here. So this is actually 1 over 7.5 is 1 over u. Whatever that gives you on a calculator, you can write that down in the results. But is there an image form at 7.5? No image. Let's just go around the table, zoom in. Let's look at it from this angle. Zoom in. All right, there. Can we push it? Push it from there? No. Another limitation of this app. You can. All right, so you're pushing it back. No image, guys. No image. Look at that. No image. So nothing at 7.5, guys. I'm very suspecting that. Okay, that looks like a virtual image there at 7.5.
Sir, magnifying glass way too close.
Well, there you go. But what is the objective of the lab, Janari? What's the objective? To find what? All right. You see, I think so. We find the focal length. It is close, but that's good. That's a good thing, because it means that we're going to the point where we can see an image. What that is telling us is that what? We have passed the focal length of the lens. That's the idea.
Sure.
Yeah. That's what we're waiting for. So we're inching up towards that mark where we want to be. All right, so moving from 7.5, let's move it up to say 8. Maybe try 9. Could try 9. Or if we can lower it down to 8.6 there. All right, no problem there. All right, no image, guys. So let's zoom out. No image whatsoever, it looks like. All right, I'm gonna assume that it's a virtual image, so we're not gonna see it No image here. All right, might make some modifications to this table as we go along. And the beauty of online thing is that we can always, change things instantly. All right, so this will be 8.6. We don't see anything. No image from yet. All right, now let's move this to like 9.7. Well, it's 9.7. Oh, we got something. All right, let's check this out. At 9.7. 9.7, guys. Nothing. But we are close. We are close. All right, we are close, guys. Oh, hold on. Was that something? Let's go closer. Nope, nothing there, guys. Nothing at all. Nothing. All right, so nothing. All right, so let's zoom out. All right, so no image at 9.7. All right, and we're gone 5 distances already, and we still don't get an image. This is telling us that we are taking our time. We are being meticulous. All right, now let's just increase this to about what 10.8. And I'm seeing that we have an image here. 10.8 gives us something, guys. So let's see, somewhere there. The objective is to be able to locate it even on the graph. And look at that, guys. At 10.8, we're seeing an image. Let's see if we can get a sharp image. All right, this image, it's actually it's diminished and inverted up until the point. Now they say we must adjust it to get a sharp image. And certainly not getting an upright image. Are we getting an upright image? Let's see. This is way magnified. Look at that. That's magnified. So big. All right. Let's go and scale it back down a bit. We're getting an inverted image here, guys. So inverted. I remember for those of you who weren't at previous class, why we say it's inverted. You see, if we look at the object, we see where the arrow is pointing. It's pointing upwards from the object. Let me just zoom out and move across here. All right, but you seeing that arrow from the object pointing upwards? All right. But the image, let's go to the image now. But the image is upside down. So
Yes, sir.
yeah. All right. Oh, that's okay. That's okay. Because we're getting an image. And according to the and that will be one of our precaution, where we adjust the position of the screen until a sharp image is formed. And sharp image, we don't want any blur image. All right. So this is a blur image. So we wouldn't record this as the image distance. All right. We want to get it sharp.
Yes, sir. Sir, when you kind of bring it down smaller, sir, can I get sharp, sir?
Very good. So very observant there. So that's blurry. That's sharp. That's sharp. We can't even see. That's sharp. That looks sharp.
Yes, sir.
Yeah. So write that down then. The question is, can you get it sharper? That's one of the source of error there. Because the sharpness of the image is very subjective on your eyes. All right. Maybe I don't have good eyes, and then you have better eyes than me, and then we're using a computer screen, and then the screen have a refresh rate and all of those variables. But then this even looks sharper. You carry anything somewhere. This is interesting. All right, so we have something at 9. There's actually 10.8. We have something there. So we have 10.8. So we're going to make an adjustment to this table though. 10.8. And we have an image All right, so we're going to subtract 10.8 from 16.7. What number you get? All right. So maths causing some problems for you guys, yeah? All right.
5.1.
How much?
5.1.
5.1. All right. You're getting a 5.1. 5.1? Sure about that?
5.9.
Oh.
Sir, 4.
Yeah. Yeah. Oh, I get a 3 different answer here, no?
Sir, it's 5.9.
5.9. I almost something 0.9 because if you take away 8 from 17 or something with 9, I go left. All right. So it's 5.9. Definitely 5.9 there. All right. So that's what we'll put for our distance. Now, I'm gonna have to do something with this table here. Feel like I should put it one side. Copy it because I want this table to have the results that you're going to use. All right, so let's put this one side. And then so meanwhile you're doing all of that, I'm just going to fix up the table so that you guys can get it to transfer it into your, whether a lab book or someone might type it, whichever way. All right. All right. Before 10.8, it was at 9.7. So I'm going to start recording from 9.7 and then do 1 over 9.7 and put that there as 1 over u. All right. Image was not farmed, so no image farm. I'm doing it for the one before this one. All right, and then now we are at 10.8. No, it's going to be 1 divided by 10.8. 10.8. And then that when give you a decimal number, you're going to write that in the second column of the table. And the image now, we just worked out. We subtracted remember now, is the distance of the image from the lens we're looking at. So you just work that out. You took away the 10.8 from the 16.7 and you get 5.9. So it's going to be 5.9 there. And of course, you're going to do 1 over 5.9 for the table. Put in the decimal number you get there. Description of the image now. Anybody can describe this image here? Describe the image for me now.
Describe the image, sir.
Yes, describe the image.
Sir, it focus on a small.
That's not how you describe an image. Give me an adjective to describe the image. One word adjective. What adjective then we use to describe the image them all the time? One word. Come on, man. Describe the image.
Modified.
What's that doing?
Modified.
Modified?
Yes, sir.
Modified or magnified?
Modified.
You can't say modified. That's not what we use to describe images. Go back to the words we keep on using. All right. If you're saying magnified, if that's the word you're trying to say, what does magnified mean?
To make bigger.
Bigger. Is the image bigger than the object that we have here? See the object here, so? Because I don't know.
The image is smaller than the object.
Then that if you say long time, so it's smaller. All right, so you say small. That's the word I look for.
Sir, then never say small, sir.
No?
You say someone will pass it in.
They say focus at a small.
You keep, but that's not saying
No, but I
anything.
just wanted.
That's not saying anything, General. You're describing the image, you say small. Me not ask about focus or
Right.
anything. Just tell me whether the size of the object. So you tell me about the size of the object whether it is upright or inverted. Those are the words you use to describe the image. And we have been doing this thing for 2 weeks now. And I'm very surprised that nobody could come up with the one word I look for. This thing here is upside down. If you even say upside down, that could have worked. But the right word for it is inverted. So the image here is inverted. And then where you say no, inverted, and you said about the size, it is what, smaller than the object. What's the word for that?
Diminish.
Diminished.
Simple.
Then use up a word, then, man. As I see, you know, when you book and shuffle to find word, you give them one word and get on to the next question. All right, so the image is, what do you say, inverted, diminished. Full stop. We can move on. Any questions?
No, sir.
All right. So inverted means upside down, diminished means smaller than the object. We are describing the image for the umpteenth time. All right, so moving on. I would say no. We'll move on to the next one now. All right, so this is 10.8 now. When increase at distance, never mind this. The screen will be, let's put the screen out of the way. We're gonna move this from 10.8 to 11.9. Let's try 11.9. And again, we're moving at small increments, right? Small distances. We're seeing that the image is certainly responding to that. So let's just adjust the screen until a sharp. Whoa, look at that. What is that? Isn't that sharp?
Yes, sir.
Yes, sir.
Yeah, we're getting somewhere. Oh, blurry, sharp. Very sharp. There you go, guys. We don't have to go further here. This is it. This is sharpness. This is the this is it. All right, let's put some measurements into this now. So this is at 11.9. Going actually. Okay. Yeah, 11.9. Yeah, go ahead. So it's going to be 11.9. And remember, in your table, you're going to do 1 over 11.9. All right. And let's look at it. The distance of image form. Distance of the image form is going to be what? This 11.9 subtracted from 72.6. What does that give you?
60.7.
Very good. 60.7. So we're going to go with 60.7. Yeah. In the centimeters there. And then, of course, remember, in your fourth column, your column beside that, you're going to do 1 over 60.7. All right. Leaving the space for that there. All right. Describe the image now.
Sir, inverse.
All right. Inverted. All right. I'll accept that. Yes, go ahead. Which other word?
Larger than object.
Yeah. Which one word for that?
Magnified.
Magnified. You see? So use the one word them describe your object them. Know what they mean. All right, these words should be in your vocabulary. So we have to reinforce it till you know say it better. All right. There's actually one description that we never put in both of them. One description missing. All right, we say it is inverted. The first one was diminished. This one is magnified. Which other word you could use to describe this?
Sir, the real image.
Very good. That's it. Real. So both of them are real. All right. So real images. And why are they real?
Sir, because they appear on the right side of the lens.
It could appear on the opposite side of the lens. Yeah. I suppose I could give you a credit for that one. Yeah. To give you credit for that one. Definitely. Definitely. All right. So yeah, it appears on the opposite side of the lens, and also it is formed from light rays actually leaving the object over here. So I'll give you that. All right. So any questions, guys? You don't understand what's happening here so far?
Yes, sir.
All right. Let's continue. Moving this from to another distance here. It was at 11.9. So let's try. This could be like 13 or something like that. Is it giving me 13? Or is it giving me 13.1? All right, let's see what happens here. 13.1. No sharp image. Oh, well, you see, for the first one, no, we have to go check out the first one now because we getting 2 sharp images. We never see no sharp image for the first one. This one sharp. If you look on it, you see that it's sharp, guys?
Yes, sir.
Because if we move it forward some more, it blurry. Right, they say sharp and it blurry. Sharp. So sharp there. Some sharpness going on there. All right. So this is so and at 13.1, guys, it's gonna be describe this. It's 55 from 55.2 minus 13.1. How much is that? Give me
2.1.
what is that? Dijane?
Sir,
What's the answer?
42.1.
42.1. All right. 42.1. All right. So let's write that as the distance of the image from 42.1. 1 over 42. Yeah. And then you get an answer there. All right. Describe the image now.
Real inverted and magnified.
Beautiful. It done. Real inverted and magnified. But you see that?
Yes, sir.
All right. Magnified. Probably not as big as the one before, but it's still magnified because this image is a lot bigger. 55 point. And what did you do a while ago? And then source error, you know. I did how much you did have it at? It was 52. 55.2. All right, man, I'll turn it around. Or zoom out. Oh, well, we can compare it. You've probably seen it now. So you see the object here, object about this height. And then the images are bigger than that. All right. So now that's 13.1. Let's increase this to about like 14.2 or something like that. Well, yeah, that's the next increment there. 14.2. Let's try that. And 1 over 14.2. We have 5 results, but we're going to go one more after this and then call it a day. It's going to be 14.2. The reciprocal of that one. All right. Let's check the image now that is from. We're looking for a sharp image, guys. Remember that. So no sharp images. Whoa, there's a sharp image. But you see that?
Yes, sir.
Yes, sir.
Sharp image. All right. Was it well? I mean, this well, the sharpest image. Again, you might want to use the first when you carry it up blurry, and the first point it gets sharp. That's the measurement you want to take. If I move it to 46.7, and then look at that, 47 centimeters. All right, subtract 14 from that.
Thirty-two point eight.
32.8. That seemed to be confirmed by other persons. So that's 1 over 32.8. All right. Description of image. Description of image. Talk to me. I know they shall know this.
Real inverted and magnified, sir.
real, inverted, and magnified. Everybody afraid to say those three words. If I say stay, I say stay, you know. All right. Real, inverted, and magnified. Yeah, that's it. All right. And then one more, because I look like, all right, I want to show you something to you know, because when it reach when is it supposed to be the same size? When is the image supposed to be the same size as the object? All right, that's one of the questions we have based on what we did since week. When is the image and the object supposed to be the same size?
When it's at 2F.
Oh, look at that, guys. You see it? Beautiful. All right. I hope everybody is listening and hear what Dacian has said. All right. When the image and object is the same size, it means that you have found 2 times the focal length of the lens. Right? That is what it's saying. 2F, 2 times the focal length. Object and image is at the same size. All right. Have the same size. So we get in there, it looks like. In fact, to find we get in there. Also, is it a case where the distance could be equal on either sides too? That's another thing to consider.
Excuse me, mom. When sir recent about the what's it called again? The lab. I'm going to ask you, can you print it Monday coming, please?
Only.
Thank you.
That's it now. All right, so this is UV lab. All right, so now 14.2, we say. Go try something. We have to go find that 2F, then want the image and object for each the same size at one at a time. So that we know that we are on the right track. That will give us the accuracy that we're looking for. All right. Now, all right. So let's proceed. And we have the data already. Move this up to like 15.3. And let's see how the image responds to that. Yeah, look at that. Get in there now, guys. Get in there. Get in there. Getting close to that 2F mark. If we don't reach it yet. All right, I could go back. All right, so that's the image on the screen, and this is the object. So hopefully you can see the two of them. See that? Get in there now, guys. Get in there. All right. So give me the result now. So we have 15.3. What is the image distance now?
2.7.
More than?
2.7.
0.7. 18, you say?
0.7, sir. 22.7.
Oh, 22. Never hear that. 22.7. All right.
27.7, I should say. Sorry.
7.7. What is happening here? All right, 27.7 you have there. All right, this is interesting. Coming down from 60.7 to 20. We're getting there then, man. We're getting there. Some may have this. All right. Let me just carry that back in. All right, press that. All right, so now we move it now to the next distance in. This probably will be 16.4 somewhere there. So you can get 16.4. Yeah, 16.4. Get a sharp image here as well. It's the sharpest image. All right, there. All right, give me the it almost look like it's same size, you know. And if they say same size, well, if the same size and same distance, all right, work out this now. We have a it's at 16.4. So take away 16.4 from 40.7. And how much 0.3?
24.
24.3. All right.
Yes.
right. All right. That's cool. That's cool. All right. Let's see. No, wait. But this no I think these are the same size. Does this look like the same size?
No, sir.
Which one bigger? Image or object?
Image.
All right, I'll go for an image. All right, cool. So, but the magnification is getting less. All right.
Yes, sir.
All right, good. So when carry it up to now 17.5. Let's see what happens. So 17.5. Can I get 17.5? Yeah, right there. Look at that. What's the same size now? Look at that. Is it the same size?
Sir, look close enough.
Close enough. All right. Well, the distance will tell us, The distance will tell us. What's the image distance? Image distance, object distance is 17.5.
22.5.
How much?
22.5.
22.5. I couldn't reach it yet, man. One, the two, one them for equal. We two of them equal. All right, let's see what's going on. So, all right. I'll move this. All right, take off that. So you say 22.5, you're saying?
Yes, sir.
All right. We're gonna run it closer now. All right, so carry to 18.6 and see what I'm now. And then image object on FICM says still 40, but we're gonna know if it farm before 40. Yeah, but this all right. It's a 38.9 it farm. Yeah, what's that now? This look at
Still not it.
I mean 38.9 minus 18.6. How much that?
20.
0.3.
I get close to it. I don't know how we not find it.
Sir, try put the object at 37. Try see if I can get no, not the object, the image, sir.
37. Let me put that 37.
37.2. Try see if I can get that.
You can get 37.2. A limitation of this. If you get 37, you can get 37. Let me see if I adjust this, I get a sharp image.
No.
Sharp at all. So they could be over. We try 37.4 then. Then see. That's the closest you can get. No, I get none at all. Gone this, Gone there. So I have this. So. No, I get a sharp image again. Unless it diminish. So all right, we could do it there. Because it was 18.6 the last one. It would have been 19.7. And sharp image just no.
Yeah.
All right, this one, yeah. All right, check out that now.
No, sir.
Oh. What am this one?
Sir, the calculation is equal.
Fairly close.
What is the image? What's the image distance for this?
19.2.
19.2. Oh, so I have this one. If you carry it you carry it to 40. Carry it to 40 now. See if you get it at the same size. Try that.
Still no.
20.3.
How much that? 20?
I'm talking about the 41, that's 20.3.
20.3
Sir,
that.
the image distance for this would have to be 39.4.
And if it's a 39, find how much?
4.
And I get 39.6 here. And we get a sharp image here. You get 39.6. 19 point something that. 19 point how much that?
19.9 that.
Close enough. Limitations though, yeah?
Sir, when you did upon the 40, it is sharp.
Yeah.
Sir, why you just don't run off the 19.7 to 20?
Yes. That we can account for that in the errors too. Yeah, good point. Good point. Both of them could be running after 20. So which means that this lab has a lot to talk about in terms of error here. But the description for this one, what would it be? Would you call it the same size? We're gonna go out on a limb and call it the same size. No. I mean, if it's a case where you're going to run it after 20, this still has some room for sharpness, you know. I mean, you know, if you look at it this way, is this the same size as the object or close to?
Yes, sir. When I say same size,
It's the same size
it's
here.
close enough.
Yeah, again, I consider the limitations of this virtual setup about there. All right. Well, all right, good. So we're getting somewhere then. So we're gonna describe this last one here as the as being what? It's gonna be real, just to see.
Inverted
Yes, good.
and same size as object.
Very good. I hope everybody is listening and understanding. Real, inverted, and same size as object. Same size. All right. So the table is filled. This table, well, according to what I have here, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 results. It's okay. CXC likes this sort of thing. It just mean that you have to go work harder to do this lab here. All right. We have some parts to finish here. We have to go get the 1 over U and them thing there. But every time I'm seeing this lab, I remember the question that they sent in June 2019. I'm trying to locate that paper, but I can't find it somewhere in my hard drive. But I remember they sent this brutal question, so that's why I have you guys doing this lab, because you know it's very likely. All right, so now we'll switch over then to the lab so we can complete it and show what that table look like.
So that's
All right, so back to this screen here. So this is the rough table here. You know, it's like a rough work. I think I'm trying to all right, we're gonna have to do some thing here. So now 1 over, well, we have a choice here. We have a choice to make here, and I'm going to change the color here, and I'm going to see if we can round off some values to make it easier for you guys. 9.7, if we call it 10, and if we call 10.8 11, 11.9 12, we call this 13, we call this 14, we call this 15, we call this 16.
so those ones in here.
Yeah.
9.5.
18.6, so you call that 19, that, and then you call this 20.
Diminished.
All right. Now, That'll be 20. We'd have 2 for 20. 20 minus 3 or 20. Some source of error did it still. All right, 22.5 out of what? 23. And then 24.3 would be 24. And we have 27.7, which will be 28. No, the reason I'm doing this is to make the calculations easy, to make the graph easier to plot. But I still would want it to write both results and put that in bracket. That's something here. Mm. All right, cool. All right, so 32.8 is 33. 42 here. 60.7 would be 61. And this was supposed to be 5.9. You got something there, 5.9.
6.
Yeah, very good, 6. And of course, this will be 0. So we have a place to start from at 0. All right, 1 over is gonna be 1 over V, 1 over U versus 1 over V. All right, let's go back to the expected graph here. It's gonna be 1 over U versus 1 over V. So yeah, all right, it's gonna be that. 1 over U versus 1 over V. Y-intercept 0 for 1 over V. All right, so it's looking good. Remember now, guys, we still have this column to fix. Them here. I'll take out them. I don't know why it's not No, so they cut out. All right. All right. So if you're gonna do it this way, we'll go to 1 over 10. We'll have to get that together, you know. 1 over 10 is 0.1. So remember, I'll go fix up that table. Put no matter. Yeah, put blank. This things are laggy. All right, so all right, 1 over. So I'll say 1 over this then. That'll be 0.1. But then we'll have to use 2 decimal place. 1 over 11, how much?
0.09.
No, 0.09. All right, 0.09. 1 over 12.
0.08.
All right, so we have one progression then. All right, no problem there. The next one.
0.07. No, 8. Guys, this is a run out.
All right. This thing keep coming up back. All right. 0.07 for the 1 over 13.
No, 8.
So 0 and 0.8 for 1 over 12 too.
Or 0.076. So she just run here.
So you're saying that the two of these run after 0.8?
Yeah. When you divide 1 by 12, they get 0.083. They run happy. 0.08.
Yeah. Okay, look at it then. All right, go on. Give me the next one.
0.07. 0.07.
Two of them are 0.07.
Yes, sir. Run off again.
All right, go on again.
0.06.
All right, hold on a minute. All right, 0.06. All right, 0.06.
Then 0.06 again.
P19, that's a 0.05.
Yes, sir. 0.0.
All right, so you know I got me answer no. Oh, I see that graph. You know, me even have no graph here for here, so if you try it out. Graph paper. I'm supposed to graph paper somewhere still. You're gonna use the screen now. All right, so all right, here you think now. This we can approach this two ways. We can since this repeat, we can rewrite the table. 1, 2. I don't know if ways we can approach this thing. I don't even know which way the best way for telling. All right, one way is to is like when you round it off over here, we use the 9.7 instead of 10, and use the 10.8 instead of 11. All right, and then we use the actual numbers and round off that. If you understand what I mean. So because we say 1 over 12 gives you 0.08. 1 over 13 also gives you 0.08. But what if we use 11.9 instead of the 12 and 13.1 instead of 13?
P11.9, I get 0.08.
All right. And for 13.1, you get what?
Yeah.
Same thing, sir.
Same thing.
0.076. Same thing.
All right. So you don't make much of a difference. All right. So that brings me to the next option then. So the next option we could do then is, all right. All right. We're going to select the ones that we're going to. So when rewrite the table and take out the ones that are repeated. All right. So like we would all right. Let me see. The one where you do for 1 over 12. What number you get for that? 1 over 12.
0.083.
83. And then all right, that sounds like it closer to the 0.08. So we're gonna use that then. We're gonna use the first 3, discard that one. Because the same thing. All right. And we use the one we're closer. Although we can just pick out randomly still. take out that. Anyone who repeat, you just use one and take out the other one after it. I'm gonna keep the 20 because that one is perfect. Yeah, that's what I do. All right. So the repeated ones, we ignore them. I'm going to keep the last one because the last one was the same size. All right, so so you're going to end up have, so if we modify that table here, we'll modify the table in, like write it back somewhere else and use that. Let me can do that now. All right. No idea. Think me have an idea. I'll go run. All right, focal length, this lab name. Where is going to be? All right, when you know lens. All right, this I go open up. All right, so now, so I'm at here, so now, let me can get for right on this. That's it now. Yeah, we can write good. Same thing. All right, so I'm gonna record it over. So you have, all right, so we call this 10, 11. Let's say it'll be 9.7. I use 10.8, 11.9, 14.2, 16.4. You go add some more things on the table. Add some more things to this now. I'll be drawing one table. Let's see something's going. Yeah, run that. All right, and then now, how much? About 2 more. All right. All right, so we have here now 16.4. We have there's one more left after that. Oh yeah, 0.6, 0.5. All right, yeah, 19.7. All right, so this will be 10, 11, 12, 14, 16, and 20. All right, and this is one over you now. So we'll just run back the calculation them again. We'll put them in back. All right, so I get 0.1 there, 0.10, 0.09, 0.08, 0.07, 0.06, and then 0.05. All right. So we need the 2 decimal places. Distance, all right. So guess what? The next part, no need for work. Now we have them already still. 5.9, 60.7, 42.1, 32.8, yeah, 27.7. 27.7, 21. I go too fast. First three, in that one, first three. All right, and we did pick out after that. So we have to go X out some of them now. So all right, we're using this one, this one, this one, X out that, use that, X that out. Use this, X out that, use that. All right, so in other words then, let's go back to that information here. So the first three is 42.1. No, 0. So my for delete all them. First one is 0. Well, at 5.9, 60.7. All right, good. Then after that is 32.8. And then after that is 24.3, and then 19.9. All right, rounded that after 20. Let's put up the round off values beside it. All right, so 24.3 is rounded off to a 24. No, 24, yeah. 24, 33, 60.7, that's what, 61. 5.9 is 6. And we're keeping the 0. All right, so now we have to go to the same 1 over V for this one. 1 over V. Well, we know say 1 over 20 is 0.05 already. But 1 over 24, how much?
Zero point zero four.
All right. 1 over 33.
0.03.
And 1 over 61.
0.016. 0.02.
And of course, 1 over 6.
0.016 to 0.02.
And 0.20 that we run after. 1/8. Hold on. Go check it again. 1 over 6 are supposed to 0.
0.17.
0.7.
0.18 that. All right. And then of course that will be 0. All right. All right. So we can we'll put back the. All right. So for all of them then, this one is no image. And then the others up to the point. But this last one here, in fact, no, not right here. The last one that we did would have been the same size. So real, inverted, same. And then all of this now would be magnified real. Inverted. All right, so that would take care of all of those. All right, so what I'm gonna do here, I'm just going to copy this table. And if I can give me the option to save as a picture. No. All right. So Word have some weird stuff. All right. Most can copy. We don't need this again. Delete all of that. Paste. And so I can hit. Yeah, put it in as a picture. And drag it down here. All right, so yeah, that's the result. So so it'll be y-axis, so it'll be x. All right, and that's it. So that's the table, guys. Table here. Very meticulous lab here. All right, so we do all of that already. The graph now. Well, they might want to see where the graph supposed to look like. Well, that's where most of the mass will be coming from anyway. So make we attack that, and then the question them can always do afterwards. But the graph now, how would the graph look? Let me just go on the other screen and find a graph paper. Or we could always use an app, GeoGebra or Desmos to draw it. That's an option too. I find a good graph paper, but I'm not seeing it. Let's see how this day. Our next slide. All right, should be there. Could have worse. All right, we'll try this then. Try out this. See a graph paper now would have set like this. Me even not tempted for use landscape on this too. If I go use landscape, I have to get a next use a next presentation. Keep it landscape. Carry the graph paper over here and plot the graph. Copy this and make it use the next one. All right. All right. Let's see how the graph will look now. All right, so we have 1 over u, and we're going to have just when label axis them 1 over u and 1 over v. 1 over u, 1 over v. All right. What else we need now? We need the results. So I'm gonna go back here. All right. Where did I click that? I'm gonna get the results from here. So that means I'm going to copy back the table. All right. Here it goes. So the table will be here. So I need for plot now. Let me make this bigger. So I can see better. All right. So I'll plot. So this is our plot here now. So this one be on the y-axis. and this will be on the X. I can just take out the thing over this one. All right, so we are plotting 1 over U against 1 over V. On the graph paper, it would look like this. All right, let's say 0.1, 0.5. That part is easy. 0.5, so no, it's not hard, man. All right, so we're going to here. But the graph paper is funny still because it's like a 10 box you have. All right. Put the 0 there, so yeah. All right, put the 0 there. And then whatever we call this.
Excuse me, sir.
Yes, Antonio.
Sir, so you recommend you download the graph paper app that you recommended, sir?
Desmos are GeoGebra. You can use that. Yeah. I recommend you download it.
All right, sir.
But when you're handing in the lab though, Antonio, yeah, you might want to draw it. You might want to draw this, because they will mark you for drawing the graph.
All right, sir.
Yeah. Because you must, all right. So remember, you must draw at least 5 graphs they're looking for. You draw with your hand. Any other graph after that, you can do it on the computer. All right. So all right. So anyway, I'm seeing where we can get a good scale here. I'm just trying to figure out the best scale. You have 0.05. If you had a real graph paper, it will be well distributed. So let's call it 0.05 then. And it's going all the way up to 0.18. So we're going short of space. Graph paper, I know the right one. Some weird graph paper we have 10. We have bigger square than usually it's supposed to have 5. The next thing, when I go do it, the only way I can go around it is if I split it in a 2. And then it will look more familiar too. See that? Split in a 2. That's nice. No, because we could have said 0. Because I say 0.01 here, so 0.02, 0.03, 0.04, and this will be over here, so that be 0.05. Then we'll get a better scale. So you can work on the graph paper, and I'm gonna give you the scale. The scale would be well, for the y-axis, for the x-axis rather, it's gonna be 1 centimeter for 0.01. That should be on the x, because we want to find a scale that goes, and this is, bear in mind that the 1 over v is on the x-axis, so we're trying to find 0.05 all the way up to 0.18. So this definitely will be 0.06, and next box will be 0.07. So we should
which view you have it? Landscape or portrait?
This is landscape.
So when you use graph paper, we can use landscape too. Right.
I can't really judge the size of the paper compared to this though. That's my problem. Since this is just a picture I may cut out, but it should work. It should work. You have a real graph paper there with you?
Yes, sir.
All right. I'll run the scale there, and you tell me if it works. So that this will be 0.10. So then 0.11, 0.12, 0.13, 0.14, 0.15, 0.16, and then 0.17, and then of course here is 0.18. All right, so this looks good. X-axis, guys, would be 1 centimeter is equal to 0.01, and that's it. For y-axis now, we want to hold from 0.05 all the way up to 0.1, which is not bad. In fact, we can go big on this one. It's like from counting from 1 to 10. So if we do that, we can go from 0. Yeah, 0.02, 0.04, 0.06, 0.08, and 0.10. We could do it that way. Or could I just go up by 1? I would have reached up the same way too. They reach up there, you know. So we could use up a graph paper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0.09, and this will be 0.10. It works. All right. So that's cool. All right. So the scale for the y-axis now looks to be 2. So guess what now? Let me see. If you're doing it on a real graph paper, I would really like to know if you hold everything. If you can hold everything for the y-axis, sorry, for the x-axis. There's actually a big axis here. You will actually need about, yeah, that look like a landscape thing still, Benito. Look like a landscape. Like a landscape. So basically, you're going to turn your graph paper. You can't know. Yeah, you turn it around. So normally it would shape straight. So you go turn it around, make it look bigger now. Your graph paper shape like a rectangle. Also, graph paper now one square. A rectangle.
Yes, sir.
So right. So you turn it now so that the longer part is facing horizontally. All right.
Let the
So
longer part be the x-axis.
yeah.
Okay.
Yeah, man. All right. So this is a start for us, guys. It's a start. It's a start. We want to plot this and show you how it looks. So according to this, you're gonna go 0.01 to 0. Sorry, 0.10 to 0. All right, 1 over u is gonna be this number up here. And let me use probably a red so we can get more highlight on it. All right, so it's gonna be 0.1 to 0 on the x-axis. All right, remember that this is our y and this is our x here. 1 over u is the y. So we're going to put an x here because it's 0.10, which is up here on the y-axis, and the x-axis would be 0, which is here. Everybody seeing the first point?
Yes, sir.
Right up here. All right, remember we use x for the points.
So
All
you
right.
only
Go ahead.
1 over you go up to 9.
Your own when you turn it landscape.
Yes, sir.
Can't fit then. I know,
But
so
if
you got eh?
if you do it to 0.01 to 1 unit, that are too short. As in, you now take up most of the graph.
Will it take up more than half of the paper?
County. Basically.
Yeah, well, use it then. If you take up more than half of the graph paper, use it. Guys, as a rule, if you're using a scale, that you can use any scale that takes up more than half of the graph paper. All right. That's it. Yeah, you're supposed to find the largest scale possible. But I mean, they don't want a scale where it's take up less than half of the graph paper. That's you want to lose marks for the scale there. All right. So just make sure that you have all of that checked out. All right. So then the first point is 0.1, which is this one, along with 0. All right. I'm ticking off the ones that are plot already. All right. So now 0.09 now should go with 0.18. All right. Now let me just look at something here. Probably was one group. And then I want to move this. I can make this smaller for the time being. Or we could say, so it's going to be 0.18 going with 0.09. 0.18 is here, 0.09 is here. This looks weird. All right, anyway. So that's ticked out. All right, now we're looking at which other one now? We're looking at let's get, should I really crap this doing now? All right, we're looking at 0.08, so that gone 0.08 and 0.2. 0.08 is here, 0.02 is here. So it's gonna be right there. All right, so we have something looking like it's going downwards. All right, and so 0.08 we say here going with 0.02. All right, so that's out. And then now 0.07 now is going to line up with 0.03. So it will be like here and 0.07, 0.03. So that line right here. So the graph looking like it's going downwards. All right, it's negative sloping. All right, and let's look at the 16 point. All right, so this one be, sorry, this will be 0.06 now going with 0.04, 0.06 going with 0.04, which would be right there. And then now, what we have here, we have 0.05 going with 0.05. That looks to be right here. So let's put that X. And then that's going to be a graph. It's a graph. All right, so if I were to plot this graph here, actually look this way. No, so yeah, so around this then. All right, so that's how it's going to look. There's one point way over here, so don't know how it reached there, but this line here is about what it should be. 9 straight because I can't use this ruler virtually. Stick it off a ruler. So it's about there. Your line would be a straight line looking like that. Any questions? That's it, you know. That's it. The graph done. One over u, of course, it's the unit for, well, it's the image distance and that measure in centimeters. But if we go 1 over u, it's gonna be centimeters to the -1. So you want to put that for your scale as a unit, and then you get mark for that. All right, this is how your graph going to look. So I'm going to take off this table now. No need that. And this is what your graph going to look like. So this is when I'm saying graph.
Sorry, take off one of the X.
What then?
You took off one of the X.
I took off one of the X.
Yes, sir.
All right, Dijane, very front here. All right. Thank you very much, Dijane. All right, let me just go back to it and adjust that. Where did one of the X go? Let me have to go put it back. All right, no problem. I don't have to put it back. It's okay. I have to put it back. Chairman, let's take off all of the you can undo so many times. Oh, that's what I was talking about. That X there.
Yes, sir.
Oh, let me see it now. Showing this one. All right, that's also the. So I'm gonna have to just select these and. All right. So yeah, that's it. So let me write the title here: graph of 1 over u versus 1 over v for our lens. In fact, it's gonna be convex lens. All right, and of course I'm putting the unit here. It's gonna be centimeters to the -1. All right, so that's what the graph should look like. Let me see if I can copy this and put it in the lab.
Sir, my plot mine, I look just like yours.
Okay, very good. Yeah, that's it. Being on the right track there. All right. So, all right, I'll drop it in here. So then, keep. Delete that one. All right, so we have this for the graph. So remember now that the mark scheme such as for the graph now: title, axis, scale, plots, and line. Line is two marks. All right, the plots, well, the plots and correct line up and so on. You get 3 marks there. Scale 2 marks. Axis label with units 2 marks. So how much that 6 and 3, 9, title and 1 mark. All right, that's all 10 marks for the lab here. All right, so that's the mark scheme here. All right, so that's a one major hurdle set. So plot a graph of this, you get the 10 marks here. So this gone. It's gone. Use a graph to determine the focal length. All right. So basically, if you go back to the expected graph, we're getting that downward slope. But not quite touching the second half, not touching the x-axis, but we still touch the y-axis, so it's close enough. They're actually saying that we have 1 over f if we mark off where the intercept is. No. This is interesting. This is interesting indeed. The focal length, this is actually 1 over f. So we're going to go back to this graph. Let's use a different color and highlight that part where them say you must use the graph and find the 1 over f. And the idea is that we would probably come here then. Somewhere here. In fact, we would actually take a measurement here. And this is somewhere here, so would be the focal length. So that'll be 1 over f, somewhere there. So, and of course, 1 over f would be here. This that's the idea here. The 1 over f would be somewhere off there. So this is interesting. No, made a mistake here. Shouldn't be that. Let me come back. So I see what happened, See what happened here. So now. All right, if this graph were to continue, it's supposed it'll touch somewhere here. So that'll be the same thing. Yeah, so that'll be 1 over f. If it were to continue the right way. And because I'm not using a ruler, this is a virtual thing, it didn't quite line up as how I wanted it to. But this will be 1 over f. Because what's going to happen is that it's going to be the same thing. See, this is 0.10, and this is actually 0.10. Hope everybody's seeing that. Yeah.
Yes, sir.
Yeah. So it's supposed to line up there. So that's a 1 over f. All right. That makes sense now. All right. So you'll get 1 mark to show this. And then let me just go back to the question as it says specifically. Use a graph to determine the focal length of the lens. So you get 1 mark for using dotted lines, which let's see like 1 over f. And the other mark is that focal length now is that you're going to actually find it. So focal length is going to be equal to 1 over f, actually 1 over 0.1. And if you do that, put that in a calculator, you end up with what, 10. Done. Hope everybody's seen that.
Yes, sir.
10 centimeter. So it basically means say if you carry it anywhere near 10 centimeter, you're not gonna see no image at the focal length. But we saw something like that happening in the lab, so we're on the right track. All right, so this is it, Let's so this part here would value 2 marks. So that's going back to this lab here, 12 marks. It's actually gonna be 12 marks combined here. So everything we will do today, ticking it off. All right. So let's see read marks. Use your results to determine the focal length of the lab. All right. So see graph. So that did. Power of the lens. All right, it's not on the CXE syllabus. It's actually on the CAPE syllabus. So but power of the lens is the same thing. Power of the lens would be the same thing as power of lens is actually 1 over f. And 1 over f for us is 1 over. I'm going with that. Sorry about that. Power of lens is 1 over the focal length. So no, why? No, we need to drop off. All right, so 1 over power of lens, guys, is 1 over focal length, which you just found out to be 1 over 10 centimeter. So that will be 0.1 measured in diopters. All right, this is slightly more advanced than CXC, but it's just how you do it. All right, Magnification now is the next big thing here for this one because we have to go work out the magnification for these three distances. Let me hold that and eat all of that. Magnification. So guess what? Magnification formula. Magnification is equal to what? Image distance over object distance. So you describe some of these images as being magnified. All right. You're going to find out how magnified it really was in at least three cases. All right. So image distance over object distance is how you find that. So let's look at, if we go back to the table. Come on. Somebody drop off. On the next page, man. Did I make something missing off of the table there? Oh, maybe it was copied from the last page. Okay, that's all right. This is the table then. All right, what we're going to do here, rather than keep going back to the table, I'm just going to put the table here. All right, and I'm going to pick out some values from the table. Remember three distances. All right, we have magnification taking place here, so, here, so, and here, so. So we could use those. I'm going to change this for 2. Change this to 2 to make it easier for you guys, because this was a key plot that I stepped down for CXC. All right. Let's delete that one. All right, now, how do I do this now? Image distance over object distance. So I take all right, so I take this distance here. We take 11. We're gonna take 6. All right, 11 and 6. All right, guys, we're taking 11 and 6. Hope everybody's seeing that. 11 and 6. So when the image, all right, so when the object now, hold on now. Go back to it again. There's something wrong with that table. Image of 6. No. Image of 60. 61 and 12 values. 61 and 12. So one of them was 61 and 12. So when you go back to the table, you'll see it though. One of them was 61 and 12. So one of them was 60 and then 60 centimeters. And the object was just 12 centimeters away. And then you end up with something like 5. Because 12 into 60 goes 5 times. So the magnification is 5. And then now, our next one now, go back to the table and see what happened there. That was the biggest one. So we select the biggest one, which is this 61 here and this 12. All right. So that was when we had the lens 12 centimeters away from the object and the image was 60 centimeters away. So we use the image distance over the object distance. Hope everybody's understanding that. And we're going to take another one that was magnified as well. When the object was at 14 centimeters, another image was formed at 33. So that's another magnification that we're going to show them, say, well, we know what we're doing. All right, so let's go again. So it was 13, and let's go back again. It was 13. So yeah, actually 14 and 33. So it will be 33 for the image and 14. All right. Also 33 centimeters. Object was 14 centimeters. So it's image, object, distance. All right. And then 14 over, so 33 over 14 is how much?
2.36.
Good. 2.36. That's it. Magnification has no units, guys. There's no units, right? The units will cancel out. So that cancel out that. That cancel out that. Just a number. All right. So there you go. That done. How much marks to that now? Probably about 6 marks to that. So you're good. So you get 3 marks for each magnification. We calculate. All right. So that'll basically we get you see that's where you're going to get marks for analysis and interpretation. Anything with graph and calculation, that's analysis and interpretation. So you have to say we give you the marks for that because I work it out and show you. All you're going to do now is organize it properly on your own. And give it back to me. All right. These are things that you would know. Focal length. I'm pretty sure persons know what focal length is, the definition.
Yes, sir.
All right. But the power of the lens. Let's look at power of lens. I'm going to all right, you know what? I was going to take it off now, but yeah, power of lens. See, power of lens is sort of something where it have two definitions though, but you know, I take off that. I take off it. Keep something this. By the power of lens, basically, the definition for it is just saying that it's the reciprocal of the focal length, but I don't have enough as it is already, so I appreciate it. So just cut out that part, and then me turn me more closer to CXC. So I need for focal length here. All right, focal length. Give the definition there, and then remember that focal length is a distance. All right, so you guys going to need to just go back to your notes and give me the proper definition for it. But it should have something about distance in the definition. All right, explain the meaning of the terms depth of focus, accommodation. Let me know. You're going to research that. So, you know, that's easily available here. These terms relate to the camera. So how camera works. So, you know, you're going to research depth of focus and tell me what that is. All right, accommodation, same thing as related to the eye. This is a lot of biology here. But long-sightedness and short-sightedness. You hear about those terms before. Some of you probably long-sighted or short-sighted already. All right, so this is something here. As a matter of fact, let me just give you a little hint here. What's I have here? All right. All right, so let me see something there. Okay, there you go. Let's find something here. All right, put it right there. All right. All right, so lift that focus here. Suppose it might be. Make it smaller. About 12. All right. All right. So lift that focus here. You have a definition there. All right. So that's because the term might be a bit technical, so kind of helping you out with that one. All right. Distance between two extreme points behind a lens, which an image is just should be in focus. All right. So discuss that more later on. Accommodation. John, accommodation. Accommodation have so many definitions. Guys, it's the one that relates to the eye. All right. I don't want anybody to write that it's housing or something related to that. It is related to the lens. All right. So remember that. All right. All right. So this is just a simple definition here. All right. See it here? So this is what it is. The ability of the lens to focus from distant to near objects. All right, then I don't think you know. So I find out this discuss that. All right, discuss means of correction. So I find out that. So all right, Monday, we're going, not Monday, Tuesday, we're going to close off this. And yeah, we're going to close off this on Monday. And then hopefully going into something new. All right, any questions, guys?
No, sir.
All right. Remember recall the source of error them. Remember say source of error them. You have to have those. All right, so all right, so like errors. So when Antonio drop out. Sunday. Errors in determine so errors in determining in distances in image and object distances. All right, that is remember when we couldn't we had some uncertainty as to whether the image was sharp in some cases, so that was one. All right, the other source of error, that's what we say the all right, well, come up with one a little more. All right, precaution now. Steps we can take to reduce these errors. So we'll make sure we do.
Adjust the position is I think I don't remember. Adjust the position of the sun until the sharp object is formed.
Yeah. In fact, that's two then. Let me just write them down. All right. So yeah. So All right, so adjust screen until a sharp until a sharp image was visible. All right, and then of course adjust object distance, all right, in small increments. All right, you could say for this one, just put algorithmic errors. All right, up limitations. Well, yeah, we have limitations, but we discuss that.
Yeah, sensitivity, I cursor.
Suppose, yeah, you could say that, yeah. Okay, I did mention that. Of course, yeah, use to adjust distances. Yeah, was problematic. All right, so there was no way of reducing this. Limitation again is like a source of error where you can't fix. All right. Conclusion. Focal length was found to be you should get 10 centimeters. So that's it. Reflection what you learn from the lab. 2 marks of that. That's it. We finish here. We finish here. All right. So let me just transport this in. I want to know if this table is actually complete. All right, hold on a sec.